Welcome to my discussion about the trapezoidal rule. Now, if you're trying to approximate areas under curves on graphs, for example, we draw our x and y axes and just draw some graph, a bit like a cubic here, and let's imagine we need to find this area. Of course, if it was flat across the top, we would just have a rectangle and there'd be no problem. We'd multiply the length by the breadth and have it very, very simply. But now we're starting to talk about trying to estimate the area under a curve. And the first and most simple estimation is achieved using the trapezoidal rule. Let me write the title. Now, before we go any further, I want to comment about why it's called the trapezoidal rule. There's a little bit of a disagreement in mathematical circles about the definition of a trapezium and a trapezoid. And the divide seems to be that Britain and its derivatives, that's the British Commonwealth and nations influenced by the British Empire, have adopted trapezium as a four-sided figure with one pair of parallel sides, for example. Historically, it seems that was the definition up until 1795 throughout England and Europe. And a trapezoid had no parallel sides, so it was just a fairly nondescript quadrilateral, a four-sided figure. In 1795, Charles Hutton, who was English, an English mathematician, wrote a dictionary of mathematics and philosophy, or mathematical and philosophical terms. And in it he made a curious remark. He said that there was some dispute, or at least people were using this term trapezoid to refer to either shape. And then he went and defined or explained that the trapezium was this shape. And his particular textbook became a very popular textbook in the United States for quite a long period of time. In fact, I think it was something like 60 or 70 or 80 years. And from that time on, based on this textbook, people in the United States and its derivatives have termed this shape the trapezoid and this one the trapezium. So this makes it awkward for me as a mathematician in Australia. I call this a trapezium and this a trapezoid. If you happen to be in the United States, I ask you to forgive me. This is just the way I learned it, and you'll just have to make an adjustment, as I do when I read mathematics textbooks from the United States. Now, interestingly, this rule is named after this term, and it's obviously named by someone who used this term to describe this shape with a pair of parallel sides, because we have a pair of parallel sides parallel with the y-axis. So that's just a little bit of a commentary about why it's called the trapezoidal rule. Now, how do we estimate the area? Well, you might recall from my previous video, or one of my previous videos, that the area for what I call a trapezium is the average length. So we average the two lengths and multiplied by the breadth or the width of the trapezium. Now here you start to see why in my original videos I avoided using the term height. I don't like using h for, I suppose one could use it for a horizontal distance, but I don't like using the term height when I'm talking horizontally. I call this the breadth and two lengths. Now, if this happened to be, for example, from point 1 to 3, so that the breadth of this particular trapezium, that's drawing a straight line across here, the breadth will be 2. I would have an area of 2 times, and let's say that the function value here, or the length here, was 5 and the length here was 4. I would simply put 5 plus 4 over 2 and find the average length of the this particular trapezium. And of course I could divide these 2's out and the answer would be, I'm running out of space at the bottom, the answer would be 9 units squared. And that, in its glory and basically, is the trapezoidal rule used for estimating the area under a curve by saying we will actually find the area of the trapezium or the trapezoid by joining these 2 points and saying the curve's fairly close to that. It's quite simple. I'll point out a few features. First, I like to write the word units squared at the end. It's on graph paper, so we're not using centimetres, metres, feet, yards, miles, nautical miles, parsecs or anything else. But just to be consistent, by writing units squared we get in the habit of writing some kind of units whenever we're finding an area. And I encourage you to do that so you never get confused, you always write something. The second thing I want to observe is that the letters or the symbols we use here in a sense are immaterial. It's the structure that we're using. We're finding an average length times the breadth. Now, in this part of the board, I'm going to remove this. In this part of the board, I'm going to show you the kinds of terminology used in various textbooks. And you'll probably recognise what's in your textbook. I encourage you to use what makes sense to you. Some textbooks do this. They replace the 1 and the 3 with A and B, and they refer to this as the function value at B, and this as the function value at A. So consequently, their area will be approximately, the area under the curve will be approximately the area of the trapezium, or the trapezoid, which will be, I'll put it in my order, which is the lengths first. It'll be the average of these times this distance. And the distance between 2 numbers is always the difference between them, B minus A, the biggest number minus the smaller one. With some textbooks you'll find the B minus A in front, and some of them will actually have the 2 under it, so you'll see something like this. So that's using your function values. Some textbooks will replace the function values with y values and call it y1 and y2, or y0 and y1 is very common. And they'll just refer to this as the height of the trapezium. So they will say the area is approximately the height times y0 plus y1 over 2. Or they might have the height here. Commonly the height is put first. These are 2 very common ways of expressing exactly the same rule. And it's simply the average height, or the average length, times the width. The average length times the width. It's however you happen to label the diagram. Function notation is very common, so is the y notation. This isn't. I have seen people use A and B. I've seen this used in textbooks. So let's write that in. A and B. So the area would be approximately the height or the width times the average length again. And the average length I think you'll see is A plus B on 2. And you could put the 2 out here or even the half in front. So all of these are very common variants of the trapezoidal rule. I encourage you to use this understanding of finding the area of a trapezium to understand the terminology that you've found in your textbook, and I hope that makes you comfortable with it. And all you need to do when you're using the trapezoidal rule once is to use those three values. Now I'm going to erase this and show you the use of the trapezoidal rule for a multiple number of trapezia. I might do it with 3 very, very quickly, and that would be sufficient for this video. But I hope that's helped you understand the trapezoidal rule simply. Let's just look at this last example. Here we have an example where we're going to find, or at least approximate, the area under a curve, a very simple one, which is a parabola, by dividing the area into 2 strips. One strip will be between x equals 1 and x equals 2, this strip here, and the other one will be between 2 and 3. So let's use this as a simple example. Now, a little comment about the formulae you find in textbooks. We would say that the area is approximately, if we're using y notation, we might call this y0, y1 and y2. These are the 3 altitudes or the 3 function values. And you can see that the width of each strip is 1. I'll represent it by h, which is what is common in textbooks. So you'd find that the area of the first strip would be h on 2, y0 plus y1, or y0 plus y1, plus the area of the second strip would be h on 2, y1 plus y2, because y1 and y2 are the lengths of the second trapezium. Actually, if we had a third one, let's put that in. This would be y3, and we'd have plus h on 2, y2 plus y3, because we've got y0, y1, y2 and y3, and we average these two to find the average height of that trapezium, or trapezoid. And what textbooks commonly do is they take this h on 2 out the front, and they recognise that we have y0 plus y1 plus, and then the next term h on 2 is multiplied by y1 plus y2, and then in the third strip we have h on 2 multiplied by y2 plus y3. And you can see that this expression is y0 plus, and we get 2 lots of y1 and 2 lots of y2 plus the y3 at the end. Why is this? Pardon the play on y. But why is it? It's because this y1, for example, is used once in the first strip to average the height for it, and then it's used in the second strip when we find the average height for it. Similarly, the y2 is used twice, one in this strip and once in this strip. The ones at each end, of course, are only used in the strip that they adjoin. Now, if this goes on and on and on, the short way of writing it in a lot of textbooks is this: h on 2, y0 plus, and let's say it goes on for an indeterminate number, we'll call it yn, and then we say it's twice all the other y values. And sometimes it's written as in here as y1 plus y2 and so on. Sometimes there are other symbols to say that you're using twice all the other y values. But the first and the last y values are used once, and then twice all the other ones. If you're using function notation, so instead of y equals, if you're using fx equals, then we might have a function value here and a function value here and a function value, and the expression would be written h on 2. The first function value, now this can be denoted in a range of ways. I'm going to call it the function value at A. Let's imagine we're going all the way to Z. The last one will be the function value at the Z end, and we will have twice all the function values. I should use braces here. Function value at B, and function value at C, and function value at D. All these are going to be used twice, of course, because for all the intermediate strips they're going to be used once in the left strip and once in the right strip. And it's only the very first and last that will only be counted once. So there it is with Y notation, with function notation. There are variants on these, and I hope this at least makes it clear and helps. Some people even resort to this. I'm just going to remove this from the beginning and say, hearkening back to my formula for the area of a trapezium or a trapezoid, H L1 plus L2 on 2 plus, and we're going to find a second one and a third one. And how do we differentiate between them? We can put a 1 as a subscript here, a 2 as a subscript here, and a 3 as a subscript here to say the first strip, the second strip and the third strip. And then substitute the two lengths and the width or the height, or if you wanted to use my formula you would use breadth. What I'm trying to explain is that I have seen a range of terminologies in different textbooks. There is sadly not a universal kind of terminology used, and consequently it pays you to be aware of the different forms and be comfortable with them, but to see the same essential structure inside them. And for some students who had difficulty with this, I've been quite happy recommending they just treat them as 3 separate trapezia and find their separate areas and add them. They still get the same answer with the same concept underlying. So let's do it with this particular problem. I'll erase this, solve it, and we're finished. So let's do that. Now, because I've got this simple form written at the top of the board, I will leave it there and I'll use this version. And in this particular equation, what are our two lengths? What are our two y values? We could have called this y1 plus y2. What are our two function values? If we put 1 in the formula, we get 1 squared plus 1. 1 squared is 1 plus 1 is 2. Sorry, plus. And what's our second length here? Put in 2. 2 squared is 4 plus 1 is 5. On 2 times the breadth of that strip is 1. I'll put times 1 in. It is a bit redundant, but we'll put it there. Plus, and now this one, we're going to use the two lengths for our second strip. Well, we've already found this one, it's worth 5. You notice here it is. When we substitute 2, let's substitute 3 for the other side of the second strip. Substitute 3, 3 squared is 9 plus 1 is 10. Multiplied by the width of the second strip, which is 1. So there's our first strip, the area of our second strip, plus the area of our third strip. Now it's going to have the length here when we substituted 3, which we've already done, and the length here when we substitute 4 is going to be 4 squared, 16 plus 1 is 17, times 1. That's going to give us 7 over 2. I'll just leave that as is. 5 plus 10 is 15 on 2 times 1, plus 10 and 17 is 27 on 2. Well, let's add the big numbers first. 27 and 15 is 30, 42, and 7 is 49 on 2. Now half of 50 is 25, so half of 49 is 24.5 units squared. This is not the most mathematical expression. It is more preferable, certainly if you're working at a higher level of mathematics, to use the function notation or the y notation rather than this. But this is perfectly adequate demonstration of the trapezoidal rule, where we use 3 trapezia to find the area of the three formulae rather, to find the area of the 3 trapezia which closely match the shape of the curve for this parabola. And we say the area is approximately 24.5 square units. If you understand calculus, you might integrate this and find the area exactly and compare it. I hope that's clarified the trapezoidal rule for you. The next video I'm going to look at the rule that the mathematician Simpson created, Simpson's rule, and I think you'll find that my explanation makes very clear sense of that particular rule. It's one that students find very confusing at times, and I think you'll find my explanations very clear. So please be on the lookout for that. If you want to know when it appears, subscribe to my channel, and by all means I'd love you to like this video and to comment on it as well. Thank you for watching.